Okay, so the main object of this talk are going to be rings, and I don't expect everyone to know what a ring is. I think most of you probably do, but that's not something you need to know. A ring is just a set of this talk is going to be a set of numbers that is closed under addition, subtraction, and multiplication, but not necessarily division. What you should think about the integers. So the integers, if you add two integers, you subtract two integers, you multiply integers, you get another integer. But if you divide, 5 divided by 8 is no longer, it's not an integer. So you get outside that set. Now, 5 divided by 8 lives in a bigger universe. It's a field. It's a rational number. But in this talk, all rings will be assumed to be commutative. So AB equals B times A. There are rings of matrices where that's not true, but we won't talk about those here. A field is what you get when you have a commutative ring where you also are closed under division. So in the integer example, if you divide, you get rational numbers. The rational numbers are a field. An ideal of a ring is a very important substructure throughout this talk. And it's a subring. So it's a subset that's also a ring, but it has one extra property that is closed under multiplication from anything in the ring. So when you see ideal, what I want you to think about, if you're not an expert on this, is think of like the multiples of some number in the integers. So in the integers, all of the ideals have the form, they're generated by one element, and this you can think of as the multiples of t. So for example, the integers are the multiples of 1, the multiples of 2, the multiples of 3, the multiples of 6, the multiples of 4. These are all ideals. They're closed not just under multiplication from each other, but also from anything else. If you take a multiple of 4, you multiply by anything in the integers, you still get a multiple of 4. You okay with this? Now, when you have a picture like this, what I like about this is you can read things like GCD and LCM right off the lat. So if you have A and B, like 4 and 6, the GCD, the greatest common divisor, is the generator of the smallest thing that contains both of these. And the least common multiple is the generator of the intersection of this. So when we have a ring like this, and when all of the ideals are generated by one element, in other words, in English, all of the substructures are the multiples of something, you can read divisibility and factorization right from this picture. So rings that have this property where every ideal is we call principal, generated by one element, are really, really nice. They're called principal ideal domains or PIDs. So I think most people here know that, but I want this to be inclusive to everybody. And also some of you, it's been years since you've taken an algebra course. The most important rings that we'll look at in field in this talk are called quadratic fields. The quadratic field, if you have a square-free integer n. I say square-free because if it's not, you can just factor out. These are the form. So the quadratic field, we say Q adjoined root m. And that's just a set of all numbers. Let me put this up here. So of the form A plus B root m, where A and B are irrational. Okay, so this is closed under addition, under subtraction, under multiplication, and it's not too hard to see it also under division as well. Okay, good. Now, all of these fields, and also in this talk, I'm only going to consider one for n is negative. So, so this will be a complex number. Every one of these fields has an associated ring of integers. And I say associated, think of this as like a degree 2 analog of the rational numbers. Because I'm taking the rationals and I'm including a root of a degree 2 polynomial, which is root n. So all of these things have an associated subring of integers which are, in plain English, the roots of the monic polynomials that live in this field. So when you have a quadratic, we have a degree 2 polynomial, you b, or the roots are negative b plus or minus, b squared minus 4ac, 2a. So whenever this thing is equal to m, all roots of monic polynomials have discriminant equal to m are in the ring of quadratic triangles. So the definition of this, it actually depends on whether or not m is 1 mod 4 or 2 or 3 mod 4. 0 mod 4 is not square root. So it turns out that if m is 2 or 3 mod 4, then the roots of the monic polynomials have the form z adjoint root m. And that's exactly what you think it is in terms of the set here. So this is z adjoint root m is a plus b root m, but now a and b are integers instead of fractions. That's why this is bracket and this is brackets. So if n is 2 or 3 mod 4, then this is precisely the roots of monic polynomials in this field. But if n is 1 mod 4, you get more roots of monic polynomials. You get these half integers. And the takeaway from this slide, what I want you to think about, remember, is that this is a field, and it has a subring of quadratic integers, which is to that field like how the integers are to. So it's like a degree 2 analog of the standard integers. So in number theory, when you want to people study these things, and now the question to ask is, there's a lot of things we know and love about the integers that we don't even think twice about. Basic properties. Some of these carry over to these quadratic integers, and some of them don't. And when things go wrong, strange things happen. So that's the idea, is study properties of these higher order quadratic integer rings. And this is quadratic. You can do this for cubic, quartic, etc. This is just the most basic, non-trivial example. Here's how I want you to think about these rings. So when r is -2, that's 2 mod 4. The quadratic integer rings are, they look like this. They're at the integer latitudes. This grid, the width of the grid is 1, and the height of the grid is √2, which is 1.41. See that? So these dots are literally the roots of the monic polynomials, where the discriminant, b squared minus 4ac, is -2. Now, -7, this one, is 1 mod 4. So this is where these are the roots of monic polynomials, and this is what they look like. So because it's 1 mod 4, you have these half integers, and you get this like triangular lattice. And I call these white because these are the invertible elements, 1 and -1. This is a unit circle. And basically, as n gets, let's say, bigger or smaller, as n gets further, more and more negative, these things get stretchier and stretchier. See that? So this is like -14. It gets even smaller. And the good rule of thumb is, as it gets stretchier and stretchier, more bad things tend to happen. Any questions so far? Yeah. Question.
I don't really understand this.
Well, that's good. You're back,
Yeah. What does it mean, the diagonal lines in the second graph?
What?
What do you mean, the diagonal lines?
Oh, I've just drawn these grid lines. It's just to show that this is a triangular. And the gray here are the ones that have happened. It's just for visual. Okay, so I'm going to show you a couple more pictures for examples. Now the next picture I'm going to show you is for n equals -1. These are called the Gaussian integers. And now my dot means something different. So that when m is -1, this grid is square. Okay. And the Gaussian integers are at these integer lattices. The black dots this time are the primes. The white dots are the invertible elements, 1, -1, I, -I. The black dots are prime. By the way, I'm gonna say a few white lies in this talk. Some of you will catch it. Things like you can't take the square root of a negative number, but like the Macauley version of that. So a prime. So this is an analog, higher degree analog of the regular integers. We know what primes are, right? In middle school, you learned about primes. A number is prime if you can't factor it into a product of two smaller. Same thing here. This number you can factor as a product of two smaller Gaussian integers. This one you can't. So all the black numbers here are prime. I'm not going to tell you how I got that. There's ways to classify these. But yeah, so these are we call them Gaussian primes. Any questions about this? This ring was studied a lot, I think, by Gauss to when he wanted to study something called quadratic reciprocity. There's a harder problem which is called cubic reciprocity, and for that you need to look at what are now called the Eisenstein integers, and that's this picture when n equals -3. So this is 1 mod 4. So once again, the quadratic integers are at the lattice points. This time there's actually 6 invertible elements on the unit circle. Only time that happens. And then the black dots are the primes. So that just means that you take one of these black dots, it doesn't factor as a product of things of smaller normal. Now, I said something slightly technically correct, but maybe misleading. Remember in 6th grade you learned what prime meant? That's actually not what prime means mathematically. So what I'm saying about doesn't factor is actually I'm saying these numbers are irreducible. You can't break them up into smaller components. Technically, in algebra number theory, what prime means is a different condition. P is prime if P. Let me move it over here. P divides AB implies P divides A or P divides B. So this is what prime means. And you look at this and it's like, well, why is this? Is this the same thing? Well, I think the best way to see this is to look at 2 examples. I had this on in case. Okay, so click 5. 5 divides 15. Or let me say A times B. So do you agree that if 5 divides A times B, that 5 divides A, or 5 divides B? So if you have a number that 5 is a prime factor of, it has to be a prime factor of either A or B. But prime means A. But 6 divides, let's say 4 times 9 is 36, right? But it's not true that 6 divides 4 or 6 divides 9. So this is not one. So when you see this in these examples, what you're really thinking of in your head, you go back to prime factor, right? The reason why this works is because you just factor a number into its prime factors, and they have to belong to one of these, either A or B. Well, that example is misleading because, so when you're doing this example, you're factoring things, thinking of a factorization. But the problem is that factorization does not have to be unique in all of these quadratic integers. So 6 is equal to, so let's do this. In Z, adjoin root -5. So things of the form A plus B root -5, if you prefer root 5I. Let's take 6. 6 is 2 times 3, right? But it's also equal to 1 plus root -5 and 1 minus root -5. And these are irreducible. You can't further break this thing up. Or you can't further break these things up. So you can't talk about the prime factorization of this. And so 2 are irreducible, but they're not prime because use that definition. If 2 divides 1 plus root negative 5 times 1 minus root negative 5 divides this product, but it doesn't divide either of these. That's something you can check. Yeah, there's tools to do it too. Yeah. So this 2 is not prime in this ring. So 3 times 3 is equal to 9. But it's also equal to 2 plus root 5 and 2 minus root 5. Negative 5. And when this happens, when unique factorization fails, you get ideals that are no longer principal. So if I mix and match, if I take this 2 and this, or if I take this 3 and this root, or 2 plus root negative 5, that together defines an idea. I cannot get everything in here just with these 2 elements. And when I say get, so the ideal generated by A and B is the set of all AX plus BY, where X and Y are in my ring. So I can't get the entire ring with just linear combinations of in this case, 3 and 2 plus root negative 5. This is an ideal. If I multiply anything in here by anything, I stay in there. But it's not the entire thing. And it is not, this thing is not the set of multiples of one element. If it were, then that element, the multiples of that element would divide both of these. And there's nothing that divides both of these except 1. So basically, when unique factorization fails, you get non-principal ideas. That will be important. And conversely, when you have non-principal ideals, I gotta be careful what I say. For quadratic integer rings, you get unique factorization things. But basically, when you have non-principal ideals, divisibility and factorization is no longer just like very nice. You can't just read it off once. Like here, remember the GCD is that. The LCN is that. Doesn't work here. The GCD, not gonna work. So a rings where all ideals are principal, you don't have any of these 2 generator ideals, are called principal ideal domains or PIDs. They're very nice. And that's what we want to understand. So let me write that up here. Because I see it. PID, all ideals are of the form, say, D. You have no 2 generator ideals. So here's a picture of that ring again, where unique factorization fails, z adjoining root negative 5, and by the way, to show you is, so once again, the integers are at the lattice points. The black numbers are the primes, and I mean actually primes using the definition of prime. So all these are the primes. Remember, 2 is not a prime, 3 is not a prime. You have to go all the way up to you have to go up to 11 to unintentional reference there. You got a prime. Sorry, it's not gonna find. I'll have some of your pop culture. Now the red dots are the irreducibles, like 3. You can't break them up further, but unique factorization fails. So here you can see 3 times 3. See this red circle? 3 times 3 equals 2 plus root 5. That's 2 minus root 5. So because you have multiple elements on circle of the same norm, you get you get non-unique factorization. So similarly, 4 plus root 5 times 4 minus root 5 is equal to 1 plus 2 root 5 times 1 minus 2 root 5. And so forth. And then the purple dots are non-primes, but I won't get into it. Unique factorization actually works. There's a ramified prime factor, and then the blue dots are the ramified primes. The couple of you who knows what that means. So see how this is stretchier than the other one? Okay. So now, so unique factorization is the first thing that I just told you about that holds for the integers. We don't even think twice about it, but they fail on some of these rings. I'll give you another one that sometimes fails, usually fails. Something we also learned about, I don't remember, middle school, high school, the division algorithm. Now, if you have two numbers, A and B is non-zero, you can divide B into A and get a quotient and remainder. When do you guys learn this? Was that middle school? I don't remember. High school.
11th grade, Tennessee.
Tennessee. So like what? What's that in non-Tennessee? Not Tennessee. Okay. I don't remember. But anyway, so as an example, let's divide 5 into 23. So what that's 4 with a remainder of 3, right? What you're doing is you're starting with 0 and you're just adding 5, 5, 5 until you get within distance 5 of 23. And most people would say that's 4 with a remainder of 3, but it's actually not unique. You could take 5 steps and you say it's 25 plus -2. So there's actually multiple ways to do this. This is actually a stronger condition than being a PID. We say that the integers are a Euclidean domain because Euclid was the first one that did this. Think back in 2,200 years ago in the Elements, he actually used this to write down an algorithm to find the GCD and LCM and other things. So it's called, so rings that have this property are called Euclidean domains. Every Euclidean domain is a PID. Basically, why is if you take an ideal like this generated by A and B, you have to prove that this can actually be generated by a single element. So what do? You take all things like this. Well, you divide B into A, and you get R, which is so A equals BQ plus R. So R is A minus BQ. So now the ideal generated by R is going to contain the ideal generated by A and B. So if it's equal, you're done. If it's not, you can just keep repeating this process. And eventually, whenever you have an ideal, basically, if you have 2 elements generating an ideal, you do the division algorithm until it stops, and now you have an ideal generated by 1 element. Yeah. I said it's wrong. What is the other thing? This is bigger than this. Good. Oh, wait, it's smaller. Sorry. Yeah. So numbers that are smaller generate more multiples bigger things. So like 2 generates, so the multiples of 2 generate contain the multiples of 6, the multiples of 10. So yeah, so the smaller elements we can get, the bigger the ideals are. Right? Do this right? That would imply that A and B are negative. But A and B are what?
Well, it's certainly true that the other containment holds, right?
Yeah.
Because R is a linear combination.
Yeah. Oh. See what you're saying.
Yeah.
Yeah. Okay. I'm not. Yeah. Sorry. Yeah. So R is A plus B. Let me erase this and add to that. Yeah. So R equals A minus BQ means that R is in there. So that means that R is in the ideal generated by A, B. Because there's a linear combination of these things. And so that means that every multiple of R, which is this, is, yeah, there. But anyways, you repeat this process and you eventually get that there's a single generator. Okay. Here, so are we again? I can show this picture to a high schooler who's learned this, and then they can understand what this is. Right? What this is doing. Let me give you this picture in the Gaussian integers. Suppose you want to divide 1 plus 2i into 6 plus 3i. Well, if you're taking 1 plus 2i steps, you're going in that direction, right? If you're taking negative steps, you're going in that direction. But you can also take steps in the I direction, and then negative I direction as well. And so the fact that the Euclidean algorithm works means that I can get inside this by taking lattice steps. Or I take lattice steps. Sometimes there's actually 3 ways. Here there's just 2. This point, this point. Here there's 3. 1, 2, 3. Now, this is a nice way to visualize the Euclidean algorithm in this field, in this ring, but it doesn't really help us understand why it works. Because if I change B, the grid's going to change. But the circle's going to get bigger too. So like it's kind of a race. It's not clear why this is always going to work as the grid gets bigger than the circle gets bigger. But and by the way, here's the failure of this in this rule. So if you try to divide 2 plus root negative 5 into 5, there is no lattice point that is strictly inside this disk. You want the boundary, that's not good. You need the remainder to be smaller. But I'm going to show you a nice way to see exactly when the Euclidean algorithm holds. So I claim that it's Euclid. Well, let me say this first. This is what we need for the Euclidean algorithm to hold. The remainder can be equal to 0, or the norm could be just smaller than the norm of phi. And n by here is just it's just the norm, complex norm. White lie there. Got it. It's fine. It's the square of the norm, but think of it as the norm. So this condition, if you divide through by b, is this condition. And let's unpack what this says. This says, if you take any a and b, and I divide b into a, well, think about this picture here. So I take an a and a b, and I take the quotient. I'm going to get some complex number with rational coordinates. Rational. This works if there is some quadratic integer q, some lattice point that's a distance less than 1 from that dart. So I throw a dart on this board. I say, is that less than 1 from one of these lattices? Here's a picture. For n equals negative 5, the answer is no. For n equals negative 15, the answer is no. These are not Euclidean domains. You have an a and a b, you take the quotient, you end up in there. You cannot find a remainder. You don't, the division algorithm fails. This is a very nice picture of a Euclidean domain. Here's the remainder of my talk. Remember that PID condition that is stronger? All ideals are principles. I'm going to give you a modified condition involving disks of different size that will tell you precisely what this is. So here's several more examples, just kind of for fun to look at. This is n equals negative 2. The unit balls clearly cover everything, right? This is a Euclidean domain. You can see it visually. This is not, this is one we just saw, or n equals negative 5, because there's these gaps. This is not a Euclidean domain. These are the rectangular cases, 2 and 3 mod 4. Let's do the triangular ones. This is the Euclidean domain. n equals negative 11. The unit balls cover the entire plane. This one's not. Now, I could have done negative 15, But this ring is going to come up later, so I wanted to do it now. So you can see there's gaps here. This is Euclidean, that is not. Here's the cool thing. That's actually a PID. There are very few, as far as I know, PIDs that are not Euclidean. Yeah, four. Four imaginary ones. Yeah, there's yeah, I don't know about higher order, like higher number fields, but yeah. So for quadratic number fields, there are actually only 4 PIDs that are not Euclidean. So there's a theorem that was proven by Kiegner in 1952, I think, a German mathematician, and it wasn't really accepted. I don't know if it wasn't understood or wasn't accepted or appreciated until Stark. He published it in German, maybe that's why. And then Stark published it in 1967 that says for m being negative. Oh, let me just say one thing. I've been saying m is negative because if m is positive, this field consists of just real numbers. It sits on the real line. And then you don't have this nice geometry. And things get a lot harder. And you also have, instead of having like 2 invertible elements, you have infinitely many of them, and they're a lot harder to analyze, they're a lot less understood. So that's why n is we're saying n is negative. So so the Stark-Kiegner theorem says that n is negative, then there are exactly 9 values of m that give you a PID. The 5 Euclidean ones obviously do. We can just look at those unit circles and say, yeah, PID. So, but remember, as n gets further away from 0, you get stretchier and stretchier. This starts happening. So there's these Euclidean domains, but then there's also 4 non-Euclidean domains that are PIDs. And this is something that I think most grad students in their first year grad course, many undergrads, hear about in passing. When you learn about all these types of domains, you learn that R-19 is a non-Euclidean PID with no explanation for why. I know I didn't understand it until like very recently. Very recently. There's a proof of it in some books. Like, so Dumb and Foote has a proof of it, but there's a whole bunch of cases you have to check, and it's not very intuitive. And then the other 3, they don't even try. Really, what happens is you wait till you take algebraic number theory, and then you have these big hardcore tools like the class group and the Minkowski bound, and then you can do some work and you can show that these work. But the elementary way is actually, I asked ChatGPT about it. It actually gave me a pretty decent response for this one, but it's a lot of cases and various. So this is what I showed you about. This is the geometric condition of being a Euclidean domain. Okay, you saw the unit balls. So the remainder, there's a remainder if and only if this unit ball condition holds. Here's the condition for a PID. It's more general. It's saying this is doing Dedekind and Haas. So the PID, if they're now we're not looking for a remainder, but if there exists P and Q for which the norm of this element is less than the norm of B. In plain English, what this is saying is in this ideal generated by A and B, if we can find an element, this is positive, but you might as well make it negative because you multiply to negative 1. If this ideal contains an element of smaller norm, it's a PID. So whenever we have, so you got this ideal of 2 elements, you want to show that you can always find, you show that this is really generated by 1 element. If you can always find a smaller norm, an element of smaller norm, then this thing is going to be a PID. In other words, the multiples of, I'm going to say wrong. You just leave it. Now, notice that Euclidean domain condition is precisely this condition when P equals 1. So if P equals 1 works, you're good. Euclidean. So this is like a more general condition. For the rest of the talk, think of P as an integer. Even though this could be even though this might not be a non-real number, we're going to think of P as an integer. So this condition, like, again, we can always find something in there that's small. that's smaller norm. That means it's got more multiples than its PID. So we do same thing we do here. We divide this time by P. This condition looks like this. And now it's saying we take A and B, we take the quotient, and we get some rational thing in the plane. So we throw in a dart in the complex plane. If that quotient A, or if that A point A over B lies within distance 1 over P, not of Q anymore, but of a P dilate, P-fold dilate of Q, then it's a PID. And let me show you a picture. So go back to this. So here is Z adjoining root -5, which is not a PID. But I'm going to try to use this visual argument. So this ring, because there's just these black points here and the black points here, and so forth. Good there? The elements of this ring are these black lattice points. The red lattice points are the half quadratic integers. It's what you get when you multiply each of these by 1/2. Is okay with that? And same thing here. And then the blue lattice points are the 1/3 quadratic integers. So the elements of the form, these things these are the red points, and then the blue points are these. So what this condition right here, even for a PID, holds if equivalently this condition holds. What this says is, well, if we're inside one of these black circles, the Euclidean algorithm works for A and B. If A or B ends up in one of these blue circles, this condition holds for P equals 3. And if we end up in one of the red circles, this condition holds for P equals 2. So why is this not a PID? If this whole thing covers the plane. It's that. This norm has to be less than the norm of B, but it can't be 0. And this thing being 0 means A over B is at one of these centers. So if you look at so look at these red lattice points, the centers of those. This doesn't hold for the centers because this inequality fails. So this is not a PID because that condition we need fails at these red points and only at these red points. So here's the big idea of the thought. If remember 2 and 3 are not prime, if P is prime, center works. That's the key. So if we can construct such a cover like this of balls of radius 1 and 1 over P for prime P, and it actually covers PID. That's the key. That's the other sort of thing. So if we cover the complex plane with open balls centered at these P-fold flat dilates of the integers of radius 1 over Pi, where Pi is either 1 or prime, inert, you know what that means? It just needs prime. It actually can be a product of primes too. It doesn't have to just be prime. But 1/4 will work. Then it's a PID. This is a geometric condition for when these rings are PIDs. And so this fails because we're using prime. I mean, the blue thing still works here because it's inside these black balls, but that doesn't work because there's nothing covering that. Doesn't prove that it's not a PID. Maybe there's primes we could use. Remember, the first smallest prime is 11. That's a very small radius. So given that, here's a proof that these two rings are PIDs. If you believe that 2 and 3 are both prime in these rings, then that's an elementary number theory thing. But I won't tell you why, but there's 2 and 3 are primes of both these rings. 2 is prime because these are 5 mod 8. 3 is prime for another similar region. But yeah, these are PIDs. There's your picture. By the way, here's a table of so I have the values of n, which are 5 mod 8. These are precisely the ones for which 2 is prime. Another elementary note, very fact. And these are only the square free ones, so that's why some are missing. This is the table that shows you what the primes actually are. So -5 is a denominator with 2 is not prime. But what do you notice? -19, 2 and 3 are prime. We actually only need balls of size 2. We didn't need the 3s. -43 has a bunch of small primes. So intuitively, things that have a lot of small primes are going to be more likely to be PIDs because you got bigger balls you can use. So this is a PID because ends up being a PID because we just saw. And then these are the 2 other ones that are PIDs. -67, look at all these primes in a row. And -163, look at all these primes we can use. It's got to be more than enough to do the trick, right? Right? Actually, no. Here's the weird thing. I've tried, and here's where some of the open questions are going to come up. Like, and by the way, when I say open questions, I mean these are, it's 2025. Some of these questions I'm pretty sure have never been even considered in the history of mathematics. People say, what's math research? This is a good example. There's so many little tentacles and things that there's questions you can ask. You can come up with something like this that no one's ever really thought of. I'm going to give you some open questions to think about that I have no idea how to solve because I'm not a number theorist. Some of you in this room are. But so I'm going to show you pictures like this for the other two values, -67 and -163. Okay. Here's -67. Here's -163. For this, I use balls of radius 1/2, 1/3, and 1/4. 4 is 2 times 2. Product primes. And here I use 1, 2, 3, 4, 5, 6, 7. 4 and 6 are product of inert primes. Inert just means it remains priming. Here's the weird thing. I said, okay, do I need 4 and 6? Can I just use these primes to cover? The answer is no, I cannot use them. I tried all of these primes to cover -67, and it looks like it covers, but there's something weird going on right here. That line? That line is 1/4. This is 1/4 times this distance. And this is 3/4 times that distance. So what's going on there? You zoom in. These are all the primes up to like 71. This green circle here this is radius 1/4. It's just there for reference. So this is going right through that dot. This is where if I include 1/4, this whole gap is gone. I don't need it. But if I don't include 1/4, see these little gaps? Here's my question. Do those gaps go away if I use more primes? I only tried up to 71. That's not very many primes. There's a lot more primes out there. 2-digit, 3-digit, billion-digit primes. I had no idea. My gut tells me, no, the gaps are going to stay. But I don't even know how to test this. Like, how do I tell in MATLAB or Sage to like take this cover of these 1/p radii? Does that cover the plane? If it does, I can probably see it. But if it doesn't, there's pixels. This is massively zoomed. This is zoomed in like 100. There's all these pixel issues. How do you even do that? There's no built-in functions for open covers, as far as I know. Maybe there is. I mean, you would need more mathematical. There has to be mathematical techniques developed and computational techniques developed just to attack these questions. I mean, again, if I just have to go up to 89, then maybe I just haven't done it enough. But I get the sense that like these gaps, like adding them, nothing really gets smaller. Here's another question. Let's suppose that we can show that these gaps remain. What is this gap set? Is it just a line? Does it have any thickness? Is it just discrete points? And what does that tell us about the ring? This is fundamentally different from those other two rings, even though they're one of the 4 non-Euclidean PIDs. Okay, so here's one more. Here's the last -163, using only primes up to like, again, 2-digit prime. So you have the same thing going on, but now this is at 1/6 the height. But look at this. You have this gap here, that actual thickness, or looks like it has thick. Maybe I just haven't gone far enough. At 1/4 times the height as well. Is that gap going to get filled in if I throw in more and more primes? And if the answer is no, the other one is yes. What's different about this ring than that? I don't know these questions. I don't know the tools. The tools I don't think exist. They have to be developed. I'm not sure how you analyze these sort of things. And what does such a gap mean? This is like the tip of the iceberg. You can construct these covers for non-PIDs. And there's going to be gaps, but how big are those gaps? The worse and worse they are. If you know about number theory, something called the class number, which is how badly unique factorization fails. You would expect that as the class number gets bigger, these gaps will get bigger as well. There might be more gaps and bigger gaps. There's got to be a correlation between those. But how do you quantify them? So so we call these things Dedekind-Haas arrangements. And the theorem is that and it covers, and they're covers if they cover the whole plane. So an element that brings the PID only if it has Dedekind-Haas cover. But what about if you only use primes? Do you have to use composite numbers for these last two? And then for other rings that are not PID, you can study these covers and say what sort of gaps do you have, and what do you say about the topology of the gaps? Are they connected? Are they discrete points? Do they have an interior? Are they fit like this? I have no idea, and I don't really have the tools to answer. Maybe I'll learn it. But a little backstory about this: the little theorem about unit disks, I didn't even know about. I'm writing a book on visual algebra, which many of you know. But I learned about that in Daniel Martin's job talk. He studied these Bianchi groups that involve pictures that kind of look like this, and he mentioned that. God, I didn't know that. And so when I did this, I talked to him. Our followed up conversations last month, and that led to this. And now we have a paper that we're going to send to the monthly. This stuff did not exist 2 months ago at all. So a lot of times people ask, what is math research? What is new math? And this could have been proposed 50 years ago, and maybe someone did and didn't get. Can't find it on Google. But one other thing I want to finish with is there is a visual math is not just recreation. Some people say it's a crutch if you want to learn real mathematics. But I forgot to include a picture of Terry Tao's book where he has Cayley graphs to illustrate group theory stuff, like elementary group theory. So anyone who says it's silly, I'm going to show you that. But there's a illustrating math seminar every Friday. No, one Friday a month. That's online. I encourage you to check out. I teach during it, so I can't go. People here can't go either. But there's a week-long workshop in Paris about illustrating math as a research technique next semester. Mathematical illustration. This is the unit tile. This is the Einstein tile. This is the notice for decades it was known. Is there a single tile that can, or is there a single shape that will tile the plane irregularly? And it was not known. And 2 years ago, they discovered that this thing will generate an irregular tile. So there's a lot of research involving visual math, and this is a semester-long program on this. And the third one involved number theory. And one of the organizers, actually, I think the organizer of the whole thing, is Daniel Martin's PhD advisor. And he's actually one of the speakers. He's going to be there in March. And number theory, you might recognize some of the names on this list as hardcore mathematicians, and they're not just doing visual math for recreation. They're using it as they're doing research. So I just want to, hopefully some of you take from this talk, not just some of these ideas, but a lot of these ideas are not just recreation. There's real research in here to be done. And so, Ben, thanks for your time. Any questions? Yeah, that's great.
First of all, that was awesome. So thank you. I have two things. One, could you go to slide 6?
Yeah.
I just wanted to point out something cool that I'm sure you're aware of, but you had such a great visualization of it already. Yeah. So you split it up into 6 sections.
Yeah.
By like radius here, and you already have all of the primes bolded like that. And so turns out that asymptotically, right, like all the primes are uniformly distributed in all these cones. And no matter where you take any kind of cone, say you took any 10-degree cone anywhere in there, right, you'd have 1/36th, right? You'd have exactly that many proportion of the primes in that cone. And that's specifically in the case where it's a PID where that holds. So
I don't know. Well, I'm not surprised at all that so the comment is that if you take like any angle here, you take the proportion of the primes, you like that it's uniformly rotated, right? Yeah.
So yeah, that's cool. And then my other thing was about the 1/2 z adjoint square root of -5.
Yeah.
I was thinking about this because z adjoint square root of -5 has class group 2, and so it turns out when you
By the way, that means the unit factorization only fails in the way we show, no other exotic way.
Yeah, but it turns out like if you take 1/2 and you add it to the string, or 1/3, or 1 over any rational prime that is not inert, then these rings are actually PIDs, right? So you like pass it only in this little finite step to a PID. So this was just off the top of my head. I was thinking about possibly if there's a way to kind of pass your problem to this like localization at a specific prime or something like that, but that was just fun.
So the people who know much more about this are Jared and Eric and Jen, the 3 of them. There may be a few others in the room as well who know more about algebraic number theory and factorization theory than I do. So,
Other questions?
yeah.
Why does this have to be like?
I don't know.
You like
That's
what?
why does math like this? I don't know. Like,
That's a great question. I gotta try.
are we inventing or discovering it? Jared can talk to you about that.
only like this, it's like.
So here's a fun thing. If you squint, look at this picture. You squint your eyes. There's a. This is sort of which one has the moat? They both. So one of these has a moat of like you squint your eyes. There's like a band where there's like no primes around at some radius, and like you can and there's it's not known if it's called a moat of non-primes. It's not known if there's any more of those. It's just
I think it was the last one. It was like a hexagon shape,
Oh,
right?
yeah. I'm too close to actually see it. Yeah, so there's a weird little moat of no primes. And the question is, are there any other moats like that in infinity? The primes get more sparse out there, but I don't think it's known.
So to what Jared said, okay, so the angles are equidistributed, but we don't know if the radii are equidistributed.
Radii,
I mean, like the moat, like the distance from 0. We don't know if there's a gap.
yeah, yeah. Okay.
Others. Well, so let me make a comment.
Jared.
Can I say one more thing? Yeah, it's not a super crazy number here thing. Just you mentioned visual algebra, and so were you at the MAA this year?
No.
Okay. Well, I encourage anybody who's interested in that visual algebra stuff to look this up too. But there's a keynote speaker.
Wait, MA Math Fest or local?
At High Point.
Okay, yeah, no.
There's a keynote speaker who talked about like rational numbers, what she called them.
Graph.
And it was a way basically of showing a number was rational using regular polygons. It's like a number was rational if you could take a regular n polygon of it with side lengths of an integer, and then have like smaller polygons with side length of an integer that perfectly fit inside of that original one, and it has all this visual stuff, and it's really, really cool. You might, I can send you stuff about it.
By the way, if anyone's interested, this MA thing, so once a year, like usually March, there's a local conference in the MAA sectional meeting. This year's going to be in North Alabama. if anyone, especially those of you who are interested in going into academia, I recommend going. It's a way you get to meet all the people who might be hiring you in a couple of years. You get a network, and you'll get more interviews locally than you will like in Oregon, just because of things like this. So, I think Jared, you've gone a few times. I recommend, especially if you're in academia, to go to these things. They're also fun. So sometimes we rent a bus and van and go. North Alabama is like 6 hours. That's a little far, but.
So I'll make one comment. So Matt's right about, so he's in the imaginary case, it's possibly called. In the real case,
And it's positive.
when M is positive, it's a whole different ball of wax. In fact, in the imaginary case, as the absolute value of the number of the radical is bigger, then how bad things can factor get worse and worse. And in fact, there's only finitely many for the negative case where you have PIDs. There's only finitely many that are HFDs, and it just gets worse and worse. For the real case, it's not known if there's infinitely many PIDs. Most computational number theorists would say if you look at radical P, where P is a positive prime, it's like over half, right? But it's still not known if there's infinitely many. It was proved recently, like in the past less than 20 years by Macauley, that real quadratic fields, they are Euclidean if and only if PID, with at most 2 exceptions. Right? There are no exceptions known, because even one exception would contradict the generalized Riemann
Oh yeah, some of the stuff is.
Yeah.
I mean, the generalized Riemann hypothesis.
Right, so that's, so that one's wide open, and it's a totally different ball of wax, so.
Ball of wax, right? You already. England, they say kettle of fish, and Gatlinburg, they say ball of wax. It's such a.
Yeah, that's right.
It's like a pigeon board type thing.
Okay, any other questions, comments? All right, well, y'all have a great weekend, and we'll see you next week.
Okay, you're from Gatlinburg, you're like rival?
So, I'll turn this off.
So I like this.
My dad was an architect.
I do know.